one of the things, there were one question that came up on Piazza, and which was about how is Wilcoxon. Just get rid of this. How is Wilcoxon? The table that I talked about. What is the intuition behind Wilcoxon? How does it actually work? So we'll just quickly see this from an example, and we'll also do a very quick test of how to compare data where if you have different scenarios of data sets where things are either skewed or there is a lack of normality, or if there is fewer sample size, what happens if you run a particular kind of test. Okay, so are people carrying laptops or no? No, okay, because I did not actually announce it. So because I said in the last class to carry your laptops, but okay, we are adults, right? You don't require reminders ideally, but it's okay. So anyway, I'll quickly give you an example of what it doesn't matter. This is all on Piazza. You can go back and you should be able to run it, but I'll just quickly show you where it is. So on Piazza, there are these general resources. You should be able to go and download these two files. I will first talk about the question that had come on Piazza, right? So the question was that when we talked about in lecture 2, when we talked about Wilcoxon test, what is the intuition on what it works? So, oh, it's not visible. Okay. So the question was that what is the intuition on which Wilcoxon works, and how is that table derived? So let me quickly go back and think about, remind you of the scenarios that we had dealt with. One of the first scenario was that we were only observing these kind of binary outcomes. We were in a paired setting, and in this paired setting, all we were able to take note of is whether the differences are higher or they are more or less. We started there, right? We started about talking about if you don't have actual quantitative measure of the differences, and if you just have idea about how many number of samples have either a higher difference or a lower difference, how do you go about it? So let me quickly go back to lecture 2 and lecture 3. So this was the premise on which we had started, which was that first thing that you always think about is you think about whether you're in a paired setting or you're in an unpaired setting. And then we think about, is that something which we can bring into a parametric world? If we can, then we use a parameter. If not, we use a non-parametric test. And in particular, we had talked about the Wilcoxon sign rank test, right? So this was initially what we had talked about, that your initial hypothesis is differences are either differences are equal to 0, and your null hypothesis, your alternate hypothesis is they're not. We are not talking about directions, and usually you shouldn't be very worried about directions. Actually, that partly will also answer the question that was asked on the second question that was asked on Piazza. So the reason you should not be worried about direction so much is the first thing that you should make sure is what are the p-value or what is the critical region that is reported, right? So if the region is itself two-tailed, all the test statistic that we will cover in this class will have this symmetric assumption. So if you have to derive the p-value of a directional test, if somebody gave you a p-value of a two-tailed test, you just have to half it, or you have to subtract that particular p-value from 1, half of that particular p-value from 1. So let's quickly see how to think about directions, right? So initially, if this is, I will just call this P alpha by 2, this all I will just call it A alpha by 2. This is the region which is covered here. This is also A alpha by 2. So whenever you see any of these tables, most of these statistical tables will report this two-sided p-value. If you're reported, or if you're given a two-sided p-value and your null is mu1 is equal to mu2, which essentially means difference is 0, and your alternate is non-directional, this is the p-value that you will report, which is A alpha by 2 plus A alpha by 2. What is this A? This is corresponding to your, so this, any test that you run, you will calculate a t statistic, right? This t is that test statistic which you will observe. This is what changes between the z test, the t test, and so on, right? So if you are assuming the normal, this could be z. If you're assuming this is not normal, standard variation, or the standard deviations are not given, you'll do a t. If you're not assuming anything, if all the thing that you're worried about is the sign of the changes, then you will do a Wilcoxon, number of ranks, a number of positive things. And if you're given the magnitude of that as well, you will perform the rank sum or the Mann-Whitney U test. So this is what the U statistic is, right? This is in the unpaired setting, of course, but that's essentially how overall, how to think about a test statistic. Okay, is that part clear? How to think about statistical testing overall. Like, so this is a number which you will always be able to calculate. It's a test statistic, and I'm calling it t observed. And again, it doesn't matter whether you're doing a z test or t test or any other test. What you're usually given in either through a form of a table or through form of a p-value or through form of a function in R is how to calculate this area. What is the probability of observing something as extreme as your t observed? And in the case where it is non-directional, given that everything is non-directional, and given that everything is going to be symmetric, this is implied in a, if your alternate hypothesis is non-directional, it is already implied that, because the order of the groups does not matter, right? So when I do mu1 minus mu2, I could have also looked at mu2 minus mu1. And in this case, if I observe something to be t observed, by definition here I will observe it to be minus t observed. So the direction in this case does not matter. This is something that you will decide before your experiment. You cannot decide this after your experiment. You have a hypothesis. Hypothesis cannot change after you have looked at the data. The hypothesis has to be decided before you look at the data. And in most cases, you will start from, I don't care about the direction, is it equal or not? But of course, there will be settings, right? In most cases, there will be settings where you require the results to hold in a particular direction. So let's take an example. My group 1 is control, and my group 2 is treatment. So I'm giving them a drug, and let's say I am going to treat blood pressure. Okay, what should happen here? What is something that you would want ideally to happen? Should group 1 be higher or group 2 be higher? You're given somebody treatment for hypertension, high blood pressure. You're going to reduce it. Your goal, you're developing a drug because you can reduce it. There's no way otherwise you are interested. Usually you will not be interested in any other direction. What should be your alternate? Mu1, right? It's very, very simple to see. This gets decided before you do the experiment. Now, if this is decided and somebody gave you, you already have access to a two-sided p-value for a given t statistic. So let's say the t statistic is some random number, 5, doesn't matter. Okay? This is what you're observing. The two-sided p-value for this is some p, which is 0. Maybe 15, or even better 0.12. What would be the correct p-value for this hypothesis? Half. Okay, why half? Right. So if this diagram is clear, right, most of the table, most of the software, you have to always read the documentation of the function. I'll show you what I mean by that. You always have to read it, but in most cases you'll be given a two-sided p-value. So if you're given a two-sided p-value, going from a two-sided to a one-sided test in this case is simple. I observed my observe, this was my, I will call it TWO for two-sided. The correct one-sided value is 0.06, right? Nothing very hard there. However, it could also happen so your null hypothesis has not changed, but your t observed is -5. What would be the p-value here? The two-sided p-value being what will be the p for p1 sided? Sorry. Too many changes. The alternate has not changed. The alternate is the same, except that when you observe this, right? This is something you decided before the experiment. This is something what you observed. What will be the p-value? This? Okay. Why? Yeah, so at this point, it's not a math question, right? It's a question of like visualizing and a geometrical question. What and the question of definition, right? So p-value is the probability of observing something as extreme as this given your null hypothesis is true, and that extreme is defined based on what is your alternate. Okay? In my previous case, the reason this is okay if this is a t test is this is also extreme and this is also extreme, right? In your when your null is not directional. In this case, I don't care about the direction. In this case, I only cared about the extreme being in the other side, right? I only cared about mu1 being greater than mu2. I don't want this other extreme. So I'm going to calculate what is the probability of observing something as extreme as this or above. And that's why this area which was given to me was 0.12. I took a half of this. Now what I observed is here, right? -5 is here, but my hope is mu1 should be greater than mu2. So it has to be in this, I want things to move or be true in this direction. and that probability is nothing but 1, which is the full area, subtracting this area or this area, sorry. They are symmetric, but it's this area. So you're subtracting what is the probability of observing something as extreme as this or more. And that's why by definition that p-value, if your test statistic happens to be in the other direction as compared to your alternate, will be above 0.5. There's no, I mean, you don't even have to calculate it, it has to be above 0.5. Okay. So I think somebody asked a question on Piazza about when you do the, we'll cover the intuition in just a bit, but when you in the Mann-Whitney U test or the rank sum test, let's just call it Mann-Whitney test because that keeps it clear. You take a max operation here. That max operation is that why should I take max and why not min? Why should I take max? I don't want to take max. I could take min also, right? There are only two possibilities. Either W plus will be higher or W minus will be higher. So if this is max, by definition this is min, I could have taken min as well. Why should I take max? If I take min, yeah. Okay, so if Monvi's response is that if I take the minimum, so the rank, the higher the rank is, the more is the magnitude essentially, right? Smaller values rank smaller or have smaller ranks, larger values have larger rank. So if I take the min, Monvi thinks that what will happen is overall there'll be more number of false positives because maybe if the max was here, the min will be here. Anyone else has another way to think about this? Think about what was given to you. Right, so let me go to that slide. Say that again. Okay, if you're taking this version, if you're taking, so if I calculate W max, then my p-value is this, okay, okay, and if I'm calculating min, then I have this thing. Any other responses? Why should I take man? Why should I take max or min? So when I gave you this value here, this table, what I did not tell you is this is for a non-directional test, which means that group 1 and group 2 could be anything. Like it doesn't matter whether group 1 has larger ranks or group 2 has larger ranks. My alternate is group 1 rank distribution is different from group 2 rank distribution. Okay. With that in mind, can you think about if I know that my number of data points are 9 and my rank is 44, right? Whatever that number is, like some 44 there, what does it tell me about the other number? It's we also thought about this from a normal point of view, right? We had we could approximate this as a normal problem. So there is nothing fundamentally different from what we did here. Should I take max or min or what? So let's just say let's go back to that table. If you have 9 data points, right, what will be the total sum of the ranks in this data set? 9 data points, sum of the ranks, assuming there are no tiles. Okay, how 45? Yeah, you know, like assuming no tie. Okay, so 9 are the observations. So this is 9. 1 plus, you know, you can make pairs. This will be 45. Now, if I get 44, maximum is 44. What does it tell me about the other one? No, this maximum here is 44. Your WS is 44. So you know, so if I go ahead with this operation, what this means is it has to mean this. They have to sum up to 45. It's just that the table that I gave you has the tabulation for the larger values. The table could have been generated for anything, right? What is tabulated here for the sake of ease, it's in some sense symmetric matrix, right? Because we are all that is being reported here are two-tailed p-values. So if you were to convert this, right, how do you visualize this actually, right? So you can think of this that this sum is 1. So the moment I reported 4 here, you could in principle shift it everything so that this looks normal. So I'm reporting 1 here. This is equivalent. It's just that I happen to report the two-sided p-value using the larger number, but there's no rule. I could have done the minimum as well. It has to be one of them essentially, just for the sake of keeping it easy to report. Does that make sense? So nothing special about max or min in that case, right? It can be, as long as somebody is reporting your two-sided p-value, it is going to be one and the same. Okay? Any questions? Okay, and then coming on to intuition, right? Like, so why there's so much recipe stuff going on in terms of how much you have to do, and you know, so many steps you have to do, and so on. But essentially, what you're trying to do, right? I had drawn a diagram last time, but I'm going to draw it again. Let's stick to the point that we're given again these values where let's take the unpaired example where the differences are, you know, you have two sets of groups and it's slightly easier to explain. Now I'm given two groups, right? So this is group 1 and group 2, and they have non-similar number of observations. So this is observation 1, and maybe this is P1, P2, P3, and P4. I know nothing about the underlying distribution, right? Have no idea about what does it look like. So the quickest hack that I can do is I can try to relatively put them together. Let me scramble them. Okay, I have just put them together. After that, I say that I have no idea about what the distribution is. So if I had some idea, I would have probably tried to plot them on a normal curve and would have seen whether this kind of distribution assumption follows. It's not going to happen because these are very small sizes. They don't often follow your normal distribution. So you can't do that, right? You can't invoke your z testing or t testing. What is the closest thing that you can try to do is you can say that I can still try to rank them. Maybe this gets rank 1, this gets rank 3 when I do it in arrange them in ascending order, and this is the kind of rank structure that they get, right? Now you come back to your number line and then try to say that for group 1 I have rank 1, so group 1 is 1, 3 and 7, so 1, 3 and 7, and group 2 is 4, 5, 6 and 2. And essentially, in just the way in when you do statistical testing with with or t test, you think for the gap to be maximized. If this gap is maximized, then those are two different groups, right? You're hoping that you see something like that happen here as well. This is a linear line on this, as in the line is linear by definition, but this is a one-dimensional structure where you're trying to see whether this gap that you see between the distribution of these deltas and these circles, which represent the two groups, how much gap is there overall. More is the gap, more is the difference. That is how you think about what is internally, what is it that it is really trying to do. Okay? Not convinced. This is just rank. I took the ranks of this data. I put this on the x-axis. So let's take the extreme example, right? Like, what is the extreme example for that case? What is the most extreme that can happen? 1, 2, 3, right? Yeah. So 1, 2, 3, 4, 5, 6, 7. You draw a median. The median will be here. So I'll draw a bigger triangle just to represent that median. The median is here. This gap is very high. But as you get other ranks, the median will shift, right? That's what essentially happens if you get a lot more intermingling to happen. What is the other extreme scenario? Let's draw the other extreme scenario. So 1, let them both sum to 10. Okay, I want to balance this. How will I balance this? That's a knapsack problem. So if you have ever done this, okay, 1, 3, 4, 15, 14, and 16, 7, 5. Does that work? Okay, let's see if that works. Oh, sorry, that won't work. I'm not allowed to do this actually because 10 is the maximum. Let me do, okay, 4, 6, 16, 12, 7 here. Okay, 7, 1, and a middle. We make that 4 and 5 and 3 and 2. That's 10 and that's 12. So I'm not able to get it to balance. Maybe it is possible, maybe it is not. But let's do 1, 2 and 7 and 4, 3, 4, 5 and 6. So this is not the best example, but what I wanted to do is if you have the medians now shifted somewhere here for the circle and somewhere here for the triangle, then this is now much narrower, right? So what I was looking for is a formulation where these two numbers become as close as possible, which I was not able to do, but there is one possible partition which will allow you to do that. Okay. Okay. Any other questions about Wilcoxon or rank sum or signed rank? The only difference between the signed rank and the rank sum is how this is paired setting in the Wilcoxon signed rank. In the rank sum, you are allowed non-paired setting, right? That's the only difference. We did this example for the non-paired setting. You could think about the same example for a paired setting. Okay. Any other questions? Okay. If not, let's maybe I will walk you through. If you have laptops, it'll be good if you can do the exercises side by side to get intuition. And as I go along, I will also explain how to sort of think about doing part of these experiments in R. So what I have is on Piazza, if you can go, the first thing that we will do is we will do the t-test versus Wilcoxon. It's okay if you don't have a laptop. Just when I ask, maybe you can try to think what is happening. Okay. So I have these two packages installed. Maybe you will not, right? So it's possible that you don't have these two packages installed. If I do that, you will get an error which says, let's say, something like this, right? There's no package called patchwork4. So similar to what you do in Python, when you install libraries, you can install libraries in R. The R ecosystem is much more stringent. The way these packages work are they are hosted on, similar to PyPy, they are hosted on this service which is called CRAN. It's not easy to get your packages up on CRAN. CRAN is where all the packages that you write in R are hosted. It's very stringent procedure to get it hosted there, unlike PyPy. PyPy, anyone can upload anything. On CRAN, it has to meet a lot of quality standards before it goes there. Anyway, so all these packages are on CRAN. If you don't have a particular package, you can just do install.packages. If you just want to install one package, for example, this is called tidyverse. You can just do install.packages. I already have it, so I'm not going to install it again. You can also install multiple packages at once. So in R, there are the arrays are referred to as a vector, as a character vector usually, right? So when I write C123, this is a character vector. If you are again coming from the Python world, this is equivalent to doing this. Okay, and that character vector can take anything. So it will automatically change the type if you in this case, right? So if I have two strings, it will automatically make it as make all of them string and so on. For this class, it doesn't matter so much, but this is how you define a particular character vector in R. Okay, everyone with me so far? So why am I talking about character vector? Because if you want to install multiple packages, you can pass it a character vector, which is I want to install tidyverse and I want to install patchwork. I will quickly tell you what these packages do. So tidyverse is not one package, but there are multiple packages including ggplot2, which is one of the most comprehensive graphical packages for visualizing data in R, and something called dplyr that allows you to do a lot of data munching operations. The first time you'll see some of the data munching happening on this script, by the way, it will appear very archaic, like, it will not make sense. But as you start to spend more time, you will realize that the power of doing very quick data summarization using this, right? So Python, unfortunately, is still not there yet. In fact, it's trying to borrow some of the ideas from the R world to do quick and dirty data manipulation. that's where I think R right now is very, very good. And I'll show you as I go along what I mean by that. Okay. Everyone with me so far? Everyone has these two packages installed? Okay. If you do, then we can proceed. Here, I am just setting the theme of the packages. This is not required. This will just set the theme of when you do the plotting to be a particular nice theme with good font sizes. That's what that particular function is for. Okay. So in the first example, I am generating a skewed data. You will notice that I'm not generating a normal. It's an exponential with a rate equal to 0.5. Right. So what does that mean? If I do, how do I do it? Right. So what command did I use? I use this command called rexp. If you don't know the meaning of that command or what that command does, you can always type a question mark followed by that command. So it's a chicken and egg problem that you'll need to know something to be able to search it, right? Otherwise you'll not be able to know, but you can always search how to generate exponential random variable in R. You will find some function. You can come back to your R and read about its documentation, right? So this is the documentation. You will have, for each function, you will have what does it do, right? So this allows you to do an exponential distribution, density distribution function, quantile function, and random number generator for the exponential function with rate, that's why I said the mean is 2, because the rate parameter is 0.5. So 1 by 0.5 is the mean. Okay. So there are multiple functions here, right? D is for the distribution, P is for the probability, Q is for the quantile, and R is for generating random numbers. They all have exp in common, so they can do everything with the exponential family. D is when you want to generate the density. P is for generating the distribution function or the PDF. Quantile is when you want to calculate, given a particular value, what quantile does it belong to for a particular rate parameter. And R is to generate random numbers, right? So is that part clear? D, P, Q, R. You will see the same thing for any distribution, right? So I can do R norm and I can generate normal random variables. Again, it has all that same thing common. D for density, P for PDF, Q for quantile, R for generating random numbers. Any other distribution? So you've done Poisson, so then R Poisson or R Poise. You can generate a Poisson number very, very simply with this function. You have done, have you done gamma? Not done gamma, but you can generate gamma, you can generate, again, multiple things. Any other distribution? Beta? Bernoulli, beta, binomial. Well, Bernoulli is sufficient for generating binomial. So you can generate any random number that you want. You can generate everything that you want. Okay. So very briefly, what I did is I generated two groups. They have the same number of data points, 20. Right. So this is n equal to 20. These are the number of data points, and the rate parameter for one of them is 0.5, and the other one is 0.3. Right? So not much different, but their overall mean is going to be different, right? So you can always do mean. Group 2 skewed mean is 5.44, and for group 1 it's 2.5. So you'll notice that it is not exactly 2, right? Because it's a small sample size. That in itself is an exercise. So I had asked it to generate a random number such that the mean, the rate parameter is 0.5, which means the mean should be 1 by 0.5, which is 2. And it's not quite the case. So I will increase the sample size if I want. And if I now do it, it's going to get closer, but it is still not there yet, right? So that in itself is an exercise that how do you, at what point does it start to match the property of the distribution that you want? Generally, more or larger sample size overall is good, but in this case, it doesn't matter for this example. Okay. The bottom line here is definitely you can see that when I generated them, their mean parameters are different. Okay. This one is 4.2, though I asked it to generate a mean parameter of 3.33, and this one is 1.39, though I asked it to generate a mean of 2. but you can hopefully clearly see that there are differences here, right? The mean parameter differs between the two groups. Everyone with me so far? Anyone lagging behind or not following? So the other issue is if you don't speak up, I will never know, right? So if you're having trouble, please let me know. Following? Okay. In the next step, what I'm doing is nothing but just creating these two, creating a data frame of these two values, of these two overall vectors that I created. So when you create a random number here like this is called a vector. This is a vector of values. I'm creating this into a data frame. And when I'm creating a data frame, I'm also adding one more column, which is of control and treatment. Okay. Now, when I do rep, right, what does rep do? Rep will repeat the generation of a particular thing, so that rather than typing control 20 times, because there are 20 values, I just type rep and it repeats that thing, and I have other thing treatment. So this is my another character vector. I'm literally putting them all in one together in one data frame, which is called data skew. Okay, everyone with me so far? You can always look at what your data frame is. If you do view, it will open a tab for you. These are your values, right? This is till 20, it is all control, and after that it is all treatment. Okay. Okay, the first thing I'm going to do is I'm going to just show you in the, so here I'm just generating a box plot of the control and the treatment groups. Let me quickly first walk you through what this function is, right? So here I am just generating a box plot. Sorry, this is P1, a histogram of the distribution. The way you do that in R is you use this command called ggplot. That's what is, it is part of this library that we imported called tidyverse. Here I am plotting the data frame. So this is the first input is the value or the name of the data frame. The x-axis here, AES, stands for the aesthetics. So the aesthetic of this data frame that I'm going to plot is the value, and I'm going to fill this number or this value by this column called group, right? So that fill determines how I'm going to color those bars. Now you have declared one layer, right? So if you just do this, nothing is going to happen. For example, you will see that each of the plotting command takes a plus operator here. The way ggplot works is it plots your data in layers. So when I do my first command, right, which is just, if I just copy the first line of that command till here, it is just going to plot what my aesthetics are. My aesthetic is nothing here but just the x-axis. There is no y-axis yet, right? So that's what it does. Okay, now I can add aesthetic. The aesthetic that I'm going to add is a histogram, and I'm going to say that you have to plot the default is I'm plotting a histogram of the x values, right? So by default, it is going to just do a histogram. I had already asked it to fill it by the group. So that's what it is trying to do here. It's doing a histogram of the value that I asked it to. So it's happening in layer by layer. First layer is of aesthetic, second layer is of histogram, and then I can keep adding layers if I want. The rest of the code here is nothing but beautification of this, right? That ideally is not required. In this particular part, I'm just going to show you what I do, and then the rest will automatically follow, right? So in this case, I don't like the default colors. This teal and this, this whatever that color is, pinkish, is extremely annoying. So I'm going to just fill it with my own colors. So there's this command called scale fill brewer. Brewer is a way to get much nicer colors in R or any language, right? So if you search color brewer, this is just what is the aesthetics of how to get good colors to your diagrams, right? So Again, one of the key takeaways from this course, hopefully, is you will draw nice figures. Any plots that you generate, try to draw, don't use default colors, because in most cases, they will make it look ugly, right? Yeah. The data skewed, what does it take? Is it? Oh yeah, sure. So yeah, sure. So yeah, that's a good question. So in R, you can stack vectors, right? In group 1, skewed is one vector, right? This is a vector which has 20 values. So the way it prints is it will print 19 and then this one is 20 and so on. Group 2 skewed is also a vector. If I want to stack them, stitch them together, I can stitch them by just doing that, stack them. So this C stands for concatenate, right? So concatenate vector 1 and vector 2. That's what you're going to do now. Okay, and then you get your 40 values. So I literally nothing very hard that I did. I took this and I stacked it this to, this is your 1, this is your 2, so that now you have 1 to 2 all in one vector, which is length 40. Okay, question. So if I show you this figure, it appears skewed, of course, right? So Anand will say this is what, left skewed, right skewed, positively skewed, negatively skewed, positively skewed. Okay, right skewed. Okay, skewed to the right, right? That is the longer tail, so skewed to the right. So for some reason, I like these distributions because there is a website where my name is right skewed, because it's an interesting distribution to follow. Anyway, here I will just, so if you want to run the entire command in RStudio, you put control and enter. Wherever that line is, it will run the next code block for you. So I went to P1, I wanted to run that entire command, and I did control enter, and then I just did P1. P1 will plot it on my plotting window. This is what your plot looks like. Okay, that's all good. I will do the same thing for P2, but now I'm going to plot a box plot. The reason I'm doing this is I want to see the spread of the data and see them side by side, right? So this is what your distribution looks like. I'm plotting the box plot, but I'm also plotting the points, the individual points. The way I'm doing this is by this command called geom_jitter. So let me take some time to actually explain why am I doing this, right? So if I remove that geom jitter, you can always comment your code by a particular line by hash. If I just do P2, it shows me this. It doesn't really tell me where my data is, right? So that's why if I want to also see my data, right? So the data, if I want to plot, these are points. So ideally, I would have done geom_point, right? That will allow me to plot the points. And let me show you what happens if I do that. There's a lot of overlapping, right? Because all of these points come from only one group, so they are literally stacked over this control group. So to avoid this, what can be done is the reason this is happening is because this is fixed, right? So you stack them together. These points, if I plot them, then they get stacked to each other. The way to avoid this is I can jitter them, which means I just add random noise onto your X and Y axis. And that's what this command jitter does. So that's why I don't have geom_point, but geom_jitter, which allows you to jitter. Okay, everyone with me so far? Okay, any questions? Okay, then I am going to plot the QQ plot. Okay, this is for that, again, that pinkish color is back, but anyway, you can remove it if you want. So this is for group 1, the sample group 1. What do you notice about this plot? QQ plot has been covered in the class, right? Has it been covered? Quantile, quantile. Okay. It's not a very difficult plot to understand. Basically, so how do you check if your data is normal, right? How do you visually see whether the data satisfy normality? You can always go and try to plot this, but there's no objective way to quantify that normality, right? I could have just plotted the distribution, for example, the histogram that I plotted in my P1, and it showed some skew, right? It showed this, but maybe you can still call it normal. QQ plot tries to quantify this. What you plot on the x-axis are theoretical quantiles that would come from a standard normal. So you take the standard normal distribution, you know its quantiles, right? You know at what point, if this is standard normal, you know that at this point I have my 25% of the data. I have then at this point I have my 50% of the data. At this point I have my 75% of the data, and so on, right? What you do with this data that you have, you observe the same thing. You calculate on a relative scale on the y-axis at what points, what are the corresponding quantiles, right? What is the corresponding quantile for a scale data? So for example, if I gave you 1, 3, 5 and 7, you will make it standard normal, right? You can make it what is the mean? 12, 15. 1 minus 5. Sorry. Let's make it simpler. 4, 9, 6, 16. So it's 5. 1 minus 4, 3 minus 4, 5 minus 4, 7 minus 4. Now, this is all mean centered at 0. You can calculate and you can divide it by its variance, whatever that variance is. I don't want to calculate, but let's say x. I can do the same operation for that, right? I can determine what value is my, so maybe this is my Q1, this is my Q2, and this is my Q3. Okay, I go and I plot a scatter plot. On the x-axis is my theoretical quantile. So Q1 theoretical, Q2 theoretical, and so on. This one is Q1 observed, Q2 observed, and so on, right? This is your observed but standardized. This is Q1, Q2, Q3, Q4, whatever. You will have to determine what your quantiles are. I'm just giving a rough example. If this was a normal distribution, if it did follow a normal distribution, after you standardize it, this should lie along a straight 45-degree line, right? That's intuitive. Is that happening in this case? It doesn't seem to be happening. It's actually, again, skewed here, because what is your extreme quantile onto your theoretical is something which is coming at 0. What should have been kind of -2, because there's a lot more information for the observed distribution. So you can see this deviation from the normal. And whenever you see this, it's a good sign to think about what test you're going to apply. You can apply a t-test. We'll do that, right? But usually is a good sign to say that, maybe that is not a good idea. Okay? Everyone with me? Just a test for normality, whether the data is normal or not. There are more statistical way of actually testing for normality. However, the bottom line is most tests are actually flawed in some sense. If you have enough data points, all of them will start to show normality. So technically, this is slightly hand wavy in what is normal and what is not normal. This is a good way to check it, but again, this is still subjective, right? At this point, your choice is still subjective. As long as you can justify why you made that choice, you are okay to proceed, right? There is no right or wrong answer here, and you'll see that once you do an assignment in your, once you do an exercise in your assignment, you'll see that the normality assumption is not the most strongest assumption. You don't require it actually to do your t-testing. You can get away with it, mostly. Anyway, so we will proceed, and we will in P4 plot the same thing, but again, in this case, you see there is slightly more skew towards this higher values. Okay, what am I interested in? I'm interested in finding out whether these values are, the group 1 is different from group 2 statistically, right? So I can plot all the 4 plots at once. This is using this package called patchwork. Patchwork treats each single plot as one object. I can do whatever I want with this. For example, right now I'm stacking them in 2 columns. I can stack them in 4 columns if I wanted. My screen unfortunately is not that wide, but you could, it is a very good package to allow you. Again, one thing which Python lacks is this kind of ecosystem which allows you to play around with graphs as if these are functions, right? So I mean, each, sorry, yeah, so this function called wrap plots comes from patchwork, but at this point you can do arithmetic with your plots. So P1 plus P2 means plot 1 and P2, that will stack it. When I'm saying arithmetic, I literally mean it. So I'm going to divide it, and I will have a vertical stacked plot. If I want to show them side by side, either plus works or I can do a parallel, a pipe operator, and it allows me to do this thing. I can do any sort of arithmetic. So let me try to do this. And I can try to put things. So P1 is 1 and P2, P3, P4 are like stacked in one thing. You cannot see anything, unfortunately, because my screen is not as wide, but you can do any sort of arithmetic. Okay. Question? Does basis as in like the, oh yeah, sure. I think that will work. Yeah. Let's see. I haven't tried it, but let's see. Yeah. Okay. Okay. We'll proceed. We will do a t-test, right? So the way to do a t-test in R is very, very simple. You do t.test. Group 2, group 1 doesn't matter. The order doesn't matter in this case, because we will mostly be working with the for this class. Again, we'll work with the non-directional test. But whenever you're running a function, please spend some time to read what it does, right? And the way to do is simple, question mark, right? That question should blow up in your, think of this as your brain, right? The moment you type something, that question should come in your brain. What does it do? And this is the way to answer that question, which is it performs 1 and 2 sample t-test on vectors of data. This is how you run it. This is the default. This is other ways to invoke it, and go down, and it will show you, tell you what is X, what is Y. I'm going to reduce this thing a bit. What is X? What is Y? What is your alternative, right? So you'll see that by default, the alternative, which is the alternative hypothesis that you have, is non-directional. It's two-sided. And that's true for most statistical software, that they will work with two-sided hypothesis, right? You can always make it greater or less. So let's do it and we'll see what comes out. This is not very relevant right now because we are doing we are doing a paired t-test, so it doesn't matter. This is, or we are doing a 2 sample test, so it doesn't matter. Paired will tell you, allow you to invoke Welch test or your normal unpaired t-test. Welch test is a special function of your unequal variances. So if this is not indicated, right, you can always see what is it set to, right? So if you go paired, it is set to false by default, right? It's not a paired t-test that you're doing. So if I asked you in the same setting to do a paired test, you will have to explicitly go and switch it on. Okay, so read the documentation. Then the same function there, you should, one second, let me zoom out a bit again. Variance equal is also set to false, which means that by default it runs what's called the Welch test, where the variances are assumed to be not equal. Okay, that's why any function you use, whether, again, doesn't matter which language it is, you should know what is the default values that you're using. Okay? This is by default running the Welch t-test. Okay, so let's run it. So just to be explicit, right, I'm going to say alternate is two-sided. Okay, and I'm going to say variance dot equal is false. So in R, you can get away with just typing short forms. So I'm not writing false. False is capital false in R. These are things. So I can just write F and it's fine. Similarly, I can just write T for true and that's fine. I think even, I think here also, let's see. Some functions allow for your partial matching, right? So let me make it a bit more explicit. So the two-sided p-value of this is 0.01824. Okay. Now quiz time, right? So this is quiz. I will now change it to 1. Okay. Read the entire thing here. The t statistic is 2.55. P-value is 0.01824. Okay. Okay. I want to now do a one-sided test. Okay. What will the p-value for this case? Sorry, where did I go? Oh, sorry. Huh. The t-test, the t-value is 2.55, p-value is 0.018. What will be the p-value for this code where I'm writing a less? Point. Any other options? Okay, that is one option. What is the other option? Okay, which one is it? Okay, let's see. Why is it 0.99? Why is it 0.99? 1 minus, right? You saw that the observed statistic is positive. You're already on this side. Now I'm going to cheat. That's what I did actually. I cheated and I said that no, my alternate should be that this is less. So it's like fine, if it's less than 1 minus this value is your p-value. That's why 0.99. Not clear? Clear? Not clear? 100%? Okay. So here, right, I observed this to be what, 2 point whatever 2.25, right, whatever, and in this case this was alternate, and then I said less, which means that the alternate that I'm testing for is mu1 less than mu2, which means that this difference, this difference should ideally be negative, right? This should have been on this side, but it is not. It is here. So what is the probability of seeing something as extreme as this, given this is what my alternate hypothesis is? So I'm going to move in this direction. That's why 1 minus. Okay, clear? So you can always do these experiments, right? If nothing is clear, that's the power of computation, right? So that's how you can teach yourself also that what is really happening in this case. Okay, very simple experiments to do in R. This is designed to do these kind of experiments. Okay, let me go ahead and finish the rest of the exercise. Okay, Wilcox test skewed. So again, I'm going to run this, but never run code blindly. Just see what does it do, right? What does Wilcox test do? Again, the alternative is two-sided, paired is false, exact is not there, correct is true, alternative is two-sided, nothing else I should be worried about right now, right? So I am going to do a two-sided test. So I will go and run it, and let's see what does the hypothesis look like. Okay, so here in my t-test, my p-value was 0.018. My Wilcox test value is 0.015. Okay, both are significant if your threshold is 0.05, but anything that you notice, anything that you notice, 0.015 Wilcox, 0.018 t-test. Which one is better? Given that what you know the truth in this case. You will not know the truth in a lot of cases. You know the truth. What is the truth? The truth was this. I simulated them to have different means. One of them was supposed to have a mean of 2 and it was 1.45. The other one was supposed to have a mean of 3.33, and I think it was close to 3.45. I know the truth in this case. I know that the group 2 is larger, and it is, because I simulated it, so I know it, right? So with this in mind, what do you prefer here? You know the backstory now. Which test do you prefer and why? So let me summarize it, right? So I simulated the data. I know what is the mean of group 1, which is 2. I know the mean of group 2, which is 3.33. Of course, they are different. Of course, they have to be statistically significant because I simulated it, right? I know what I'm doing. You will not know this when you observe the data because somebody gave you clinical trial data. You don't know the truth. Nobody knows the truth. In this case, I know the truth because I simulated it, right? Or you simulated it, for example. With this in mind, what would be your expectation of p-value? Like what do you really want to see? Smaller p-values, right? You want to see smaller p-values. You want things to be significant because they are. That's the ground reality. That's what you simulated this to be. And when I observe, my Wilcox is 0.015, my Welch 2 sample is 0.018. The difference is not very large, but Wilcox is still better because it's able to pick out things when I know that there is difference. And this is not a cherry-picked example. We'll do some more examples, and you will see that when these assumptions, some of these assumptions, not all the assumptions of normality start to break, if the sample size is small, if there is not much enough that you know about the distribution, then you should go non-parametric. Okay? That gives you power to detect things which would otherwise get masked out because you're forcing things to look in a non-parametric fashion. It happens to be other way around as well, which you'll probably do as part of your exercise. But we'll do 2 more examples and it will hopefully become clear. But everyone understands what we did? I simulated the data. I simulated them with different means, and I showed that in p-value, it's not extreme, right? Like I'm actually forcing you to think. But let's do some other examples. Okay, so this was a case where I had a skew in my data where the normality assumption, of course, does not hold. Let me do one more example. And now I'm going to just quickly follow through. Here I'm doing a very simple thing where I'm generating a random normal, right? So this is a Gaussian with mean 10 and standard deviation 2. This is a random Gaussian with mean 12 and standard deviation 2. Let me run it. It has 18 points. This has 20 points. The reason for that is because I am going to now add 2 more values to it at the bottom, which you can't see here. 1 second. Okay, so I am adding 2 outliers. It's a mean of 10 and a standard deviation of 2. So mean of 10, standard deviation 2 means like this is what, 2.96. So 16, right? That's where this should end. And minus 16 is where this should end. I'm adding a extreme outlier, 25 and 28. So the number of points are again 20, but these are like 2 extreme outliers in the case of group 1, which is mean 2, standard deviation, mean 10, standard deviation 2. Okay. So rather than me talking, I will just quickly show you what does this look like. So what am I doing here? And this is what I was talking about, is how do you do data munching in R? So in data munching in R is usually done with this library called dplyr. So this pipe operator that you're seeing allows you to pipe your information, right? So this is your data frame. I'm piping this information. I will explain in just a bit what is that piping to, and calling a function called group by group. So this is a function from that package. This is my data frame. Group is one of the columns in my data frame. I am grouping my data frame by this group column, and then I'm mutating. So I'm mutating my original data frame to add four values there, four new columns: Q1, Q3, IQR, and is outlier. Your Q1 is nothing but which I'm calculating the 25th percent quantile. Q3 is 75th percent quantile. IQR is Q3 minus Q1, and is outlier is if this value is beyond Q1 or Q3. Okay, this you've probably seen in the box plot version. So why am I doing this? It will become clear next, but let me quickly show you. So I created one data frame, and then here I am just mutating it. So let's just look at what does this look like. Okay, it is nothing but now you have added these values explicitly in your data frame, right? So now this has what initially was two columns. Now I've added these four columns: Q1, Q3, IQR, and is outlier. I've added four extra columns. That's what that function does. Okay, the reason I added this is because I want to plot you and show you what are the outliers. So here I am again going to plot my box plot, but I am going to explicitly annotate the labels which are outliers. Okay, the reason I want to do this is I just want to show you that there are extreme outliers in this data set. It's not required, but it's good to see, right? Those are the outliers in your data. That in first group, in these two I explicitly added, and in this it just happens to be there. You know, if it just does not follow the distribution properties of even though this is a random normal that I simulated, you can always observe like outliers based on the definition that we have. There's nothing surprising about this. Here I explicitly added them. Okay, is that clear? Okay, what do I want to do? Very quickly, I want to test whether there is mean difference between the two groups. Hypothesis being two groups equal mean, alternate hypothesis being not equal. We will do some more plots. This is just to show you different ways of visualizing things. This is P6. So this is just a violin plot, what's called a violin plot. Because it's called violin because it looks like a violin. The reason these plots are useful sometimes is a box plot only shows you where the median are, it doesn't show you the distribution. Violin is estimating the density of points as well. So a fatter distribution here means there are a lot more points here. There are a lot more points here. There are points here, but they don't have as much density. So that's why that's narrow. This is called a violin plot. Okay. And finally, we will calculate some summary. This summary is nothing but what you saw visually. This just has what is a group, what is its standard deviation, what is its mean, what is its median, and so on. Okay. Finally, I'm going to plot this value. So this plot doesn't appear to be that nice, but this just shows you that the mean of the group 1 with a drug is 11.95. Its standard deviation, the median is 11.53. This is 12.23. Median is 11.31. Before proceeding, what do you think is going to happen? I'm testing for two groups. Is the mean or the median of these two groups statistically different or not? That's the hypothesis that we have. 11.95 drug mean, placebo mean 12.23, drug median 11.53, and median for placebo 11.31. What do you notice and what stands out? Mean is higher for which one? Placebo. right? Placebo is, nothing, no change or no drug given. Median is higher for which one? Drug. Okay. How is that possible? Because of the outliers, right? The outliers are going to skew your mean values, right? So the outliers that we had added in the second group are shifting the mean, but the median will not change. So this is an example to show you both the things, that mean sometimes is a wrong metric to measure if you're comparing, because one or two outliers can throw your entire stuff off. Okay, so now we will do the t-test. So this is, again, you want to stitch columns together, doesn't matter for this example. Well, this should be 3, but doesn't matter. Okay, this is your data summary again. Mean, median, standard deviation, number of data points. Number of data points are the same between both of them. I'm going to run t-test, and I'm going to run Wilcox. Okay, let's look at t-test. What do you think will happen? Will it be significant, or will it not be? Also, by the way, just to let you know, because this usually is not as intuitive, but hopefully should be, is you can auto-complete things. If I do tab, right? So if I do tab, it will tell me what are the possibilities. So I don't have to type the entire stuff every time. If I just do type t test and just do tab, it will show me all possible values here, which are defined in my variable. Okay, t-test 0.82. Significant or not significant? Okay, that's my alarm, because I have another class to teach at 5, so we'll have to explicitly stop in 5 minutes. Significant or not significant? Not significant. Okay, what do you think will happen to the other one? Actually, I don't know. What will happen to the Wilcox test? Should be significant or should not be? It's not. What do you still notice? What do you notice? P-value of 0.p value of 0.082, and in case of t-test and Wilcox is 0.54, right? So it is not able to find, with 20 data points, none of these tests are actually able to find differences. We again know in this case that the mean was different. 10 was the mean of one group, 12 was the mean of the other group. We are not able to find it, but we again notice that the p-value here, we know in this case again that there is difference. While none of them appear to be significant, this is still closer overall to the actual truth. Okay, just one last example, which I'm going to run very, very quickly, is small sample size. Actually, 2 examples very quickly. This is small sample size with just 8 data points. The shape parameter of the gamma distribution, which you have not covered in the class but doesn't matter, is a measure of how much what is the corresponding mean of that particular distribution. I am doing the same thing here. This is a paired setting. This is what it visualizes, right? So even before I do the test, right, this is what the distribution looks like. This is some drug with some concentration or some biomarker before and after a treatment. This is after, this is before. This is what its probability distribution looks like. What do you think will happen if I test for significance? Significant? Anyone else? Why not? There seem to be some matter, right? Like some substance in overall the values. We'll find out. The issue is we have very small sample size, right? So whenever you have small sample size, collecting evidence is going to be always tricky. So I'm going to run this test and let's see what tells us. So t-test 0.1, Wilcox is 0.04. In this case, again, you know the truth. You know that this has a different shape parameter, which means it's a different mean parameter. It allows you to get a different p-value, right? So the way I simulated this example was very, very simple. I had a template. I started from that template, and then it's just thinking about different scenarios, just switching for different probability distributions that are possible. In this case, Wilcox is again what you want, because definitely here again you know the difference, and in this case you got lucky that you are actually able to see the difference only with a sample size of 8. And one final example before we stop, which is in this case, what the data is the data that we discussed, which is there's something called anyone has given her psychometric tests? No psychometric. You guys must have given psychometric test. Psychometric test? Yeah. PNG, IITC, all the FMCCs. Anyway, so yeah. So psychometric test is basically how consistent you are in life, in broad sense. It's a fun test. It does actually, well, depends on whom you talk to, but I think there is some substance to it. You're basically asked similar kind of questions again in different fashion, and all they're looking for is, are you the right person who speaks the truth in some sense, right? Are you consistent as compared to whether you're smart or not? Okay, so these values are often measured on your on a relative nominal, on an ordinal scale, and that's what this data is. Again, in this case, I am simulating this with values, explicit values here. Here I'm sampling them with a different probability. Okay, so here I'm sampling numbers from 1 to 5. The probability with which I'm sampling is different. So in this case, this is more biased towards 1. This is the probability with which I sample 1 from 1 to 30, from 1 to 5. I do it 30 times. And in this case, so 1 is more in this case, 1 is less. In this case, 1 and 2 are more. And in this case, 4 is more, right? So you again know that this is going to be, of course, this is going to be different. We do this again, we do our usual things. I will not have to worry about showing you that. But when you do the test, right, there are certain ties here, and that's why you get a warning in this case that it cannot compare exact p-value. Don't worry about it at all. Let's just look at what does this look like. So your p-value in case of t-test is 0.8455. This is Welch t-test. And in the case of Wilcox, that's again 0.844, right? So again, in a very small sample, in a smallish sample case where we are working with your usual sign rank test, we don't find significance. Rank sum test, sorry. We don't find significance. In your assignment, you come back and fix it and explain why that's happening overall in this case. So that's a good stopping point. Any questions? Okay. So yeah, the notebook for this and another thing which I've not covered, which answers the question which was posted on Piazza, is there on Piazza. The other R script, you'll be able to see how that table that I talked about is generated, right? So if you have any questions, please feel free to post them on Piazza. See you on Tuesday.